Hey everyone, and welcome to this explainer. For decades, humanity has had this incredible dream of building a permanent home on the moon and eventually leaving our footprints in the red dust of Mars. And here's the crazy thing, we actually know how to do it. The world's top engineers and academics have already mapped out the exact blueprints for our future in space. But as we're going to explore, it turns out that our earthly realities, not the orbital mechanics, are what's really holding us back.
So, that brings us to the central question of today's explainer. If we literally have the blueprints to live on the moon and Mars, what exactly is the holdup? Well, as we'll see, while the math and the physics are actually mostly solved, the execution is, well, it's pretty messy. We're essentially caught in this massive tug-of-war between brilliant engineering solutions on one side and some really gritty geopolitical and bureaucratic realities on the other.
Okay, let's dive right into our roadmap for today. We'll start with 1, the space architecture trade space. Then 2, rendezvous and field choices. 3, the Mars consensus problem. 4, blueprints versus bureaucracy. 5, NASA versus China speed. And finally, 6, the true space race.
All right, kicking things off with Section 1, the Space Architecture Trade Space.
So according to a really fascinating benchmarking study out of MIT, every single space mission essentially boils down to a set of what they call architectural decisions. Think of these as the fundamental building blocks of our space blueprints. They're the absolutely crucial choices about what vehicles we need to build, how they're going to interact with each other, and most importantly, where exactly they're going to meet up out in the void of space. Because deciding where to park a spacecraft and what fuel to pump into it, that literally dictates the mass, the cost, and the ultimate success of the entire mission.
Moving right along to Section 2, rendezvous and fuel choices.
And this brilliantly illustrates the physics of those choices. Since the Apollo days, engineers have mapped out 4 totally distinct rendezvous trajectories to get to the moon. You've got direct return, which is just shooting straight from Earth to the lunar surface. Then there's Earth orbit rendezvous, where you assemble or refuel your ship around Earth first. There's lunar orbit rendezvous, which is actually what Apollo used. And finally, libration point rendezvous, taking advantage of those stable gravitational parking spots in deep space. Now, choosing just one of these paths completely changes the entire design of your spacecraft.
To put that into perspective, just think about Apollo 11. They had a super quick surface stay of just 21 hours, right? And their lander's wet mass, meaning its weight when completely full of fuel, was about 15,000 kilograms. But when you look at modern proposals from NASA, ULA, and Lockheed Martin, we're talking about staying on the surface for 7 to 14 days, with access to the entire lunar globe. To keep a crew alive that long, the landers have to be absolutely massive, ballooning to nearly 60,000 kilograms. And that kind of heavy lifting forces a really intense engineering debate.
And that debate, it's all about fuel. The MIT study highlights this massive trade-off. On one hand, you have liquid hydrogen architectures. Now, liquid hydrogen is notoriously difficult to manage, and it makes your lander much heavier. But on the flip side, you have liquid oxygen and methane architectures. Those let you build a lighter lander, sure, but they offer significantly less mission utility across the board.
Now, what's really interesting about the math here is that it proves without a doubt that despite the massive weight penalty, hydrogen architectures drastically increase your mission's productivity. They deliver vastly more people days on the lunar surface and way more payload per crew member for the exact same number of rocket launches. So for the moon, it's pretty much a solved engineering trade-off. If you want a sustained long-term presence, you just have to bite the bullet and accept the heavier hydrogen lander.
But the moon is one thing, which brings us to Section 3, the Mars consensus problem. 18. That is the number of major Mars architectural studies from NASA, private industry, and academia that the MIT researchers evaluated. And the most shocking takeaway from all of them? There is virtually zero consensus across these 18 blueprints on how to actually design a mission to Mars. None.
To understand why it's such a headache, you have to break down a Martian lander into 4 critical steps. Step 1, the outbound transit to Mars orbit. Step 2, the crazy descent down to the Martian surface. Step 3, the ascent back up to orbit. And Step 4, the inbound transit back home to Earth. Across those 18 studies, the brightest minds on the planet literally cannot agree on which vehicle should handle which step, or even when the astronaut should be sitting inside it.
Which leads to this stunning conclusion from the MIT paper. You know how with the moon, a heavier lander essentially guarantees a longer stay? Well, for Mars, there is absolutely no clear relationship between a lander's wet mass and the length of a crewed surface stay. Actually, let me emphasize that. Simply throwing more deployed elements or extra fuel depots or heavier landers at Mars does not predictably give you a longer mission. The math for the red planet is still deeply, deeply unsettled.
All right, sharp pivot here into Section 4, Blueprints versus Bureaucracy.
Because while the physics are tough, the biggest roadblocks are right here on Earth. Just listen to this jarring quote from a public discussion regarding NASA facilities. Someone said, "We don't even have HVAC in a large amount of our buildings. We pull tarps over our laser cutter so the known roof leak doesn't damage it." I mean, wow, that is a massive contrast to those pristine, high-tech MIT blueprints, right? It really exposes the gritty reality of underfunded facilities where some of the world's most advanced engineering is supposed to be taking place.
When you dive into the public forums discussing the modern space race, the obstacles people highlight are incredibly terrestrial. We're talking about severe political red tape, massive budget constraints, and facility deterioration, like we just heard with the leaking roofs. On top of that, commenters point out a lack of a standardized, long-term vision. For example, Congress sometimes mandates the use of expensive, legacy space shuttle parts just to save local jobs, rather than letting engineers design a brand new rocket from a clean sheet of paper.
Let's see how this plays out globally in Section 5, NASA versus China speed. Based on the sources, public observers frequently contrast two very different organizational models. On one side, you have NASA, which operates in a highly decentralized way. Now, they heavily rely on incredible commercial partners like SpaceX, but observers note they're also hobbled by shifting politics and those mandates to use legacy parts. On the flip side, you have the Chinese National Space Administration, or CNSA. They run a highly centralized, heavily funded defense program. And observers point out they have the luxury of designing their launch vehicles totally from scratch, moving at what is commonly referred to as China speed.
So, the crucial point being debated out there is perfectly captured by this public observation. The very structure that's designed to secure NASA's funding, scattering different space centers all across the nation to secure votes from local congressional districts, actually creates massive bureaucratic inefficiencies that just don't exist in the centralized Chinese model. It's essentially a feature, not a bug, of the political system, but it directly slows down the speed of the engineering.
Which brings us to our final act, Section 6, the true space race.
To ultimately win this race and establish a sustained, permanent presence in space, whoever gets there first has to balance a massive web of complex factors. First, they need sustained political will, the kind that outlasts a single 4-year election cycle. For the US, it's also going to heavily depend on the ongoing success of the commercial sector, like SpaceX. Both nations have to somehow overcome severe budget and facility limits. And oh yeah, on top of all that earthly bureaucracy, they still have to flawlessly master the unforgiving orbital rendezvous physics that the MIT study outlined. So what does this all mean? I'll leave you with this provocative thought to wrap up our explainer today. We have the blueprints. The math for the moon is basically solved, and the math for Mars is being aggressively debated as we speak. But when humanity finally takes its next historic footsteps on a new world, will those steps be driven by the sheer brilliance of the absolute best engineering, or by the nation with the most unified politics? Definitely something to think about the next time you look up at the night sky. Thanks so much for joining me on this explainer, and keep learning.